Hello and welcome back to this section of HUP 112, Logic and Philosophy. My name is Richard Brown, and today we'll be discussing predicate logic, which will be the last section of this class. We won't be covering the whole chapter on predicate logic, but pretty much the first three sections of it. We'll see how far that we get. Now, predicate logic is essentially taking all of the things that we've done from propositional logic and then expanding it to include quantifiers, which have so far been left out. So you may remember from our discussion earlier that we had sentences all S are P and no S are P, and some S are P, and finally some S are not P. S and P are subject and predicate, and you remember those from our categorical terms. And we remember how we translate this, where we say all dogs are mammals. We translate that as an if-then statement. If it's a dog, then it's a mammal. No snakes are mammals. If it's a snake, then it's not a mammal. Some dogs are mammals. Some dogs are not mammals. So we need to learn how to translate these. So far we've ignored them. And if we saw something like this, we would simply translate it as A, maybe. And we haven't been able to look inside at the structure. But now it's time to get that structure back. And so with predicate logic, we need to introduce some new syntactical elements, and then we'll talk about how those things are defined. So the primary structure of predicate logic is the predicate. And predicates are going to be symbolized with capital letters. And so we're going to use predicates, capital letters, to stand for predicates. Now notice in the previous sections we've used capital letters to stand for propositions. So A might be Albert is a dog, and B might be Burbank is the capital of Geneva, and C might be circuitry is complex, blah, blah. But now they're going to be standing for predicates, and predicates express relations between things. So for instance, here's a predicate. Blank is a rabbit. That's a predicate, because this can be filled in with many different things. You could put Albert is a rabbit, Joan is a rabbit. If anything is a rabbit, then Doug is. And so we will use capital letters to stand for predicates. And so if we had a sentence that said Doug is a rabbit, Doug is a rabbit, then we would use R to stand for blank is a rabbit, and that would be our key. R equals blank is a rabbit. So that's just something that needs to be filled in. And so what is it? We use lowercase letters to stand for the things which are assigned these predicates. And so here D would stand for Doug. It'd be a name for Doug. And to write Doug as a rabbit, we would symbolize it RD, where you'd be read this thing is that thing, or has that predicate. So Doug is a rabbit, given our key here. And there are many different kinds of predicates. So we will talk about them as they come up. Okay, so suppose that you had the sentence, and so we use capital letters for predicates, and we use lowercase letters for individuals. We use lowercase letters for individuals. So that's A, B, C, etc. And all the way except for X, Y, and Z, which we reserve for variables, and we'll introduce those in a second. So suppose that we wanted to translate the statement here from the book. If Paris is beautiful, then Andre told the truth. So B, we could stand for blank is beautiful, and P standing for Paris. Then we write Paris is beautiful as BP. And if T stands for blank tells the truth, and A stands for Andre, then this says if Paris is beautiful, then Andre tells the truth. And so that is, notice that we before wouldn't have this structure, this relationship here. We might just translate that as B horseshoe T in our propositional logic, but now we can actually talk about some of the structure that's going on in there, and it allows us to introduce quantifiers and to define the quantifiers. So we have two quantifiers that we're going to introduce, quantifiers. And on the one hand, we have a symbol that we're going to write as this. It's going to be an X or a Y in parentheses. You could have it like that, or we will use Z as well. On the other hand, we have a symbol that looks like a backwards E, and then this thing, and that's in parentheses, and you could have Y there as well, and you could have Z there as well. So by convention, there's no good reason, it's just a rule that we have to pick and we have to stick with. We use X, Y, and Z for variables, and we use the other letters of the alphabet for individuals. So this here is called the universal quantifier. It's pronounced for all X, for all Y, for all Z. This is the existential quantifier. It's pronounced there is an X such that, there is a Y such that, there is a Z such that. And so now these can be used to translate our individual statements that we had before. So recall our first sentence that we just talked about. We have all S are P. We know that it's going to be translated if S then P, right? So, but what? So suppose this says all dogs are mammals. The way you would translate that is you first use the universal quantifier, SX, horseshoe, PX. And that's the way you translate this. This says for all X, if X is an S, then X is a P. So if all dogs are mammals, then for all X, if X is a dog, then X is a mammal, and so forth. Now we do the same for translating no S, R, P, and there we use for all X, if it's an S, then it's not a P. Okay, so those are our universal statements, and they're translated in terms of universal quantifiers. Now, just as a note on stylistic variations, sometimes you will see universal quantifiers written as an upside down A, and that's a perfectly standard kind of convention, but we don't use that. We use this parentheses here instead of those, but you may see that occasionally, a standard kind of A. And so this sentence should be thought of as telling us that for everything in the universe, this is true of it. So if it's an S, then it's not a P. Now suppose that this says no snakes are mammals. Okay, so S equals snakes and P equals mammals. Okay, so this says for all X, if it's a snake, then it's not a mammal. And you say, well, what if you're talking about me? What if I am the X in question? Is that sentence true of me? Yes. Well, in that case, it will be false that I'm a snake, but true that I'm a mammal. But we know from our, so that makes that false. So we know from our truth tables, though, that this combination makes the whole sentence true. So this sentence still is true of me, and it's true whether or not there are any things that this thing could quantify over. And that's very nice. Okay, so here's our two ways of representing the universal statements, all S or P and no S or P. And then we use our existential quantifiers for the other two. So if we write some S or P, some S or P, that would be translated into there exists an X such that X is S and it's also P, Sx dot Px. So there exists an X, which is both S and P. So suppose you said some dogs are four-legged. Then we translate that to mean there is an X, such that X is a dog and X is four-legged. And the same is true over here. If you say some S are not P, you would write there exists an X, which is S but not P. So now we have a way to translate our four statements from before, and now we can introduce some rules for using these. So let's go ahead and do some practice translation. These come from the book. So suppose that our sentence was that all skyscrapers are tall. So if you say all skyscrapers are tall, then you say for all X, if it's a skyscraper, then it's tall. Notice that these are the same to make sure you're talking about the same object. No frogs are birds. For all x, if it's a frog, then it's not a bird. Okay. All ambassadors are statesmen. For all x, if it's an ambassador, then it's a statesman. No diamonds are rubies. For all x, if it's a diamond, then it's not a ruby. Okay, so now we have this additional level of complication here, and we can use these to translate some arguments and use our rules. Now we need to learn an important distinction here, so that, and this is going to come up and I'll explain what it means in a second, but for now we can note the difference between this and this. So here, just as before, when this thing is in front of the whole statement, then it's governing this whole statement, so that it's binding these two variables here, and we would say that these two variables are bound by that quantifier. But here, in this case, if this is for all x, sx, then the quantifier merely binds that and doesn't do anything with this over here. So that we would say this variable is a free variable, and this variable is bound. And the difference between bound and free variables is very important and something that we will discuss as we come to it. Okay, so suppose we had the following argument. This comes from the book. The first premise says all economists are social scientists. So let's write that down. All economists are social scientists. Our second premise is that Paul Krugman is an economist. Our conclusion, therefore, is that Paul Krugman is a social scientist. Okay, so this argument clearly is a form of syllogism that is valid. So we have to translate it. All economists are social scientists would be translated. Remember the word all here is translated as a universal quantifier, and we'll use E to stand for economists and S to stand for social scientists. So the first premise says for all x, if x is an E, an economist, then x is an S, a social scientist. Our second premise here is that Paul Krugman is an economist, and we can use P to stand for Paul Krugman. And the conclusion is, therefore, social scientists. Okay, so now we've translated our argument into this more abstract form. Let me rewrite it up here. So we have premise 1, for all x, ex, horseshoe sx. Premise 2 is EP, and the conclusion is SP. Now the thing to note here is that this clearly is a form of modus ponens hanging out in here. So this is, E horseshoe S, there's E, there's S, but this says X and that says P, and they're not the same. And we cannot use modus ponens with the quantifier hanging out here. So we have to have some way to take the quantifier off and to write what we want down on the line. And we have a rule that allows us to do that. It's called universal instantiation, and we write UI when we invoke it. Universal instantiation depends on the following kind of reasoning. It's not a truth functional rule, but you have to think about the following thing. So let's take this first sentence. It says, for all x, if x is an E, then x is an S. Okay, and we've forget about what E and S stands for right now. This tells you that every object in the world, this sentence is true of. And we already sort of informally established that by saying, well, even if you're not an economist, and that makes that false, then this sentence is going to be true no matter what. So for everything, this is true. So you might think of this as, if you had a list of all the things which exists, everything which exists, you might think of this as equivalent to a statement like this. Well, if A is an E, then A is an S. And if B is an E, then B is an S. And if C is an E, then C is an S. And so you might think of this as really a long conjunction. I mean, I should have written it out like this. And this is gonna keep growing and growing, and it's gonna be as long as the list of things which exist in the world, because this just says it's true for everything. So if you think of this as a kind of hidden conjunction, listing everything in the world and stating this about it, then it's very easy to see that universal instantiation is a valid rule, because what it tells you is that when you have something like this, you can take the quantifier off and write whatever you want there. And the reasoning is that since this is supposed to be true for all objects that exist in the world, then it's true for anyone arbitrarily chosen at random or by design. So here we can write line 3, and we can instantiate this universal statement. So we can say, well, if it's true for everything, then it's true for P. And we can write EP, horseshoe, SP. And we can say we got that from line 1 by universal instantiation. So the reasoning, again, is very simple. If this is true for everything, then it should be true for this particular thing that we're interested in here. But now that we have lines 2 and 3, we can do our modus ponens. And we can write lines 4, SP, and we got that from lines 2 and 3, which are modus ponens. So universal instantiation allows you to take off the quantifier and write anything you want here. You could leave it, of course, if you wanted to, but that wouldn't help us. You could write A, B, C, or whatever. That wouldn't help us. So we use P because we had P right there. Okay. This right here is called an instantial letter because you instantiate with respect to that variable. You put something there. Okay. Okay, so let's do another one. So we have universal instantiation. We need another rule, which we're going to call universal generalization. So this allows us to take off a quantifier. This allows us to put the quantifier on. So let's translate our argument here. Our first premise says that all psychologists are doctors. Okay. Our second premise says all doctors are college graduates. Our conclusion is that therefore all psychiatrists are college graduates. So that's exciting. Now let's go ahead and translate this. So it looks like we're going to have 3 universally quantified statements. So we translate all psychiatrists are doctors. We'll use P and D. So that says for all X, if it's a psychiatrist, then it's a doctor. Fantastic. Our second premise here says all doctors are college graduates. So for all X, if it's a doctor, then it's a college graduate. Our conclusion is that therefore all psychiatrists are college graduates. So now we have 3 universally quantified statements here. For all X, parentheses, if PX, then DX. For all X, if DX, then CX. Conclusion, for all X, if PX, then CX. So you can see that there's a kind of hypothetical syllogism going on there. You can see that there's a kind of hypothetical syllogism going on there, but we need to get rid of these quantifiers. So we can use our instantiation rules. So we can write down line 3, we can take off this quantifier and write anything that we want. So we could write, for instance, Py, horseshoe, Dy. And I chose another variable here because remember, it's true for everything. So it doesn't really matter what you write down there. and that was by universal instantiation. Now we could have just left it x. That's also something we could have done, but just to show you, we could do whatever we want, that's fine. So now we have py horseshoe dy. We do the same thing here. So we write down line 4, and we're going to have dy horseshoe cy, and we got that from line 2 by universal instantiation. And the only thing that matters here is that we chose the same instantial letter. So if we chose py horseshoe dy, then we need to make sure we stick with y, otherwise we're not going to be able to do our hypothetical syllogism. So now we have them here, and we can write down line 5, py horseshoe cy, py horseshoe cy, and we got that because lines 3 and 4 are hypothetical syllogism. But now notice, what we have written here, these things here, are not really statements, because the quantifier is off and these variables are free. So in our premises, the variables are bound by the quantifiers in each case. We don't have any free variables. But by removing that quantifier, we've now freed these variables. Now this is not a real statement of English. Py horseshoe dy is not a real well-formed statement of English, because if you were to try to say it in English, you would say y, whatever that thing is, it's a variable, sort of say it. If it's p, then it's d. Okay, if it's p, then it's d, but what's it? That's not a really well-formed sentence. If you say if it's p, then it's d. People sort of know what you're talking about, but they want to know what it is. So these are not real assertions, and you cannot just leave them hanging around there. And notice that the conclusion is not py horseshoe cy, but for all x, px horseshoe cx. So, but we can add our universal quantifier here using our rule, universal generalization. And since this is a statement about everything, but without the quantifier on it, well, we're allowed to just write the quantifier back on. And so we can write for all x, substituting x for the y there, px horseshoe cx, and we got that from line 5 by universal generalization. We generalize from this because we know that this is a statement about everything. It's just sort of written in handy form, taking off the quantifiers. So we took off the quantifier, we did something, we added the quantifier back onto it. Now what's important about universal generalization is that it only works on variables. So now we're done here, but let's suppose, let's suppose we had a different premise here, 3 prime. And let's suppose I had instantiated with like PA horseshoe DA, choosing not a variable y, but a name A. Well, then it would be, and suppose I did the same thing here with dy DA horseshoe CA, that would be my 4 prime. Then I could do my hypothetical syllogism here and get PA horseshoe CA. But now notice I'm talking about A, this is something. So it's wrong to then say, well, I can go from this to the universally quantified px horseshoe cx, because this is a statement about one particular individual, A, whoever that is, Albert. But this is a statement about everything. And of course, it's not a good reasoning pattern to say, well, this is true of one particular guy, Albert, therefore it's true of everything. But that's not what's going on in these cases, because we're not talking about one particular person, but this is sort of just left in this non-grammatical semi-English form, which is what allows universal generalization. Okay, so that's all very good. Now the same, we need to add 2 more rules to this. So we have universal instantiation, universal generalization, and we're going to do the same thing for our existential quantifiers. So we need an EG and an EI. EI for taking off the existential quantifier, and EG for putting existential quantifiers back on. So here's an argument which shows that we need our EG. Suppose that the argument told you all tenors are singers. So So our first premise is for all x, all tenors are singers. If tenor x, then singer x. And our second premise is Andrea Bocelli is a tenor. So tenor Andrea. And our conclusion is therefore he's a singer. I think it's a he. Our conclusion is therefore there is at least one singer. So therefore, our conclusion is therefore there is at least one singer. Now that's clearly true. If all of the guys of this stripe are also of that stripe, and you have one, then you know you're going to have at least one of the other, this guy. But we need to prove that this is valid. So we could use our rules, universal instantiation, and we want to make sure that we get A. We can pick any letter we want. So we may as well pick A, otherwise we can't do modus ponens. Now, of course, we could write TA, TB, SA, whatever. That's not going to help us. Now that we have this, though, we can do modus ponens and get SA. Okay, and that follows. So this we got from line 1 by universal instantiation. This we got by line 3, and 1 by modus ponens. Now we know that this guy is a singer, but we want this as our conclusion. So, but this says there's a guy named A who has this property S. So if that's true, then we know that this is true. So we're allowed to use existential generalization and write down line 5 and say that, well, if that's true, then there is at least one X. We know in this case it's A, but it doesn't matter. We know there's at least one, which is a singer. And we got that from line 4 by existential generalization. Okay, existential generalization. So let's do another one to illustrate an important property of existential generalization. So look at our premise here. For all x, px, horseshoe, qx. Our second premise for all x, px, for all x, px. And our conclusion is exists an x. QX. Okay. So we want this. We can see a version of modus ponens here. So we can write down our line 3 here. And we could write, P, A, horseshoe, Q, A from line 1 by UI. We could write down line 4, P, A from line 2, UI. And then we could get line 5, Q, A from 3 and 4 by modus ponens. Now we can say, well, one thing is Q, so we know there exists an X such that QX. And I'm sorry, I always end up doing that. There exists an X such that QX, and we got that from line 5 by existential generalization. Now we could have done that, but we also could do the following thing, and this becomes important sometimes. It's not really important right now, but it might be important later, so we may as well talk about it. We could also do this. We could write down line 3, and we could instantiate with a variable. Okay, so we got that from line 1 by UI. Now we haven't picked a name, so we don't say Albert or Betty. We say Y, whatever it is. And we can do the same thing here. PY from line 2 by universal instantiation. That allows us to get QY. Now that's a variable, and we got that from we got that from 3 and 4 by modus ponens. But now we know that this says the difference between the previous one, where this was an A, is that says one particular individual has this, therefore it has that. Whereas this says everything. Remember, everything is such that if it's P, then it's Q. This says everything is P, that says everything is Q. So if everything is Q, then we know at least one thing is Q. If everything is Q, we know at least one thing is Q, and so we can say that there exists an X such that QX, and we got that from line 5 by existential generalization. So you can generalize existentially from a variable or a name or constant. It doesn't matter. Whereas for our universal generalization, you can only do that from a variable and not a name. And that's, of course, a very important difference. That's, of course, a very important difference. So let's finish off by talking about existential instantiation here. And so we'll take an argument. It says all attorneys are college graduates. Let's formalize that. All attorneys are college graduates, so we know it's going to be for all X. If attorney X, then college graduate X. Okay. Our second premise says some attorneys are golfers. So we know some, that exists in X. Some attorneys are golfers, so there's at least one thing, which is an attorney and a golfer. And the conclusion is, therefore, some golfers are college graduates. Conclusion, there exists an X such that golfer X and college graduate X. Okay, so now we have our thing here. This is what we want. Now notice, there's nothing we can do until we get rid of these quantifiers here. So the one thing that we want to keep in mind here, and I guess this will become important in a second, is that sometimes the order that you do things matters. So let's suppose that we just simply wrote down line 3 here. And by the way, you can sort of see what's going to happen here. You want to get this AX horseshoe CX written down somehow. You want to get this down somehow. You want to do modus ponens to give you CX. You want to simplify to give you GX and combine those, and then you'll have that. So we want to be able to do that, but we want to do it in the right way. So we want to do that in the right way. I'll explain this later, but we want to start by getting rid of this quantifier. And so existential instantiation has the following reasoning behind it. If this sentence is true, it says there's at least one thing that's A and also G. Now we don't know which thing that is. We don't know. So whereas this sentence might be thought of as a giant conjunction, remember, so if you might think of this as saying, well, A, then C, and B, then CB, and AC, then CC, and etc., etc., etc. So this is a giant conjunction here, and you can simplify and get anyone you want. That's roughly the reasoning behind universal instantiation. For here, you can think of there exists an X, such that AX dot GX, as a kind of disjunction. So it says, well, for every object there is in the world, it's either A dot G, A, or A, B dot G, B, or AC dot G, C, or, and so whereas before, it was a conjunction, substituting everything in the universe for the instantial letters, here's a disjunction. And so we don't know which one of those is true, but at least one of them is. And remember, that's how disjunction works. All of these could be false. At least one of these is true. The whole sentence is true. So we know there's at least one thing in the world. We know there's at least one thing in the world, which is an A and a G. So we can just name it. Let's call it George. And so we can write down A, G dot G, G. And we got that from line 2 by existential instantiation. So now what's George? George is just a name that we made up. We don't know who George is. We don't know what it is. All we know is that it's at least one thing, which is both A and G. So that we know because this sentence is true. So we can write that down. But now we can instantiate our first premise. So we write down line 4 here, AX horseshoe CX, and we can write down anything because this says it's true for every object in the domain of discourse here. So if it's true for every object, then it should be true for the thing we just named, G. So we can write down A, G, horseshoe, C, G, and we got that from line 1 by universal instantiation. Okay, so now we can simplify. We write down line 5, and we get AG. And we got that from line 3 by simplification. Now we can do modus ponens. Line 6, we get CG, and we got that from lines 4 and 5 by modus ponens. So we're on our way. Now we need to get G down here. We can get it by reversing and simplifying. So we can write down line 7, G dot AG from line 3 by associativity. Simplify line 8, G from line 7 by simplification. Now we have GG and we have CG, so there's that. And we can then write line 9, conjoin those but put them in the right way. GG dot CG, because line 6 and 8 by conjunction. Now we know there's at least this one thing, G, which has these two properties, and so we can use our generalization. And we can say, well, there exists an X, whatever it is, such that G and C. And now we're done. Okay, so notice that that's very interesting. Because the one thing we had to do here was we started with this existential instantiation. Now suppose we didn't start with the existential instantiation. Suppose that we started this way. Suppose that we wrote down line 3 and we started here. And so we wrote A, G, horseshoe, C, G from line 1 by universal instantiation. That's perfectly allowable. There's nothing wrong with doing that. There's nothing wrong with doing that. But now suppose that we wanted to say, well now we write down line 4 and we want this thing here. So suppose that we said A, G dot C, G from line 2 by universal existential instantiation. This is not allowed. This is not allowed. And that's a very important restriction on how you're able to use the existential instantiation rule. And the rule says that you can substitute this for anything you want. It has to be a name, can't be another variable, has to be a name, but it can't have appeared previously in any line of the proof. It has to be a name that doesn't appear on any line of the proof. So you can't do this and then move to this. Notice we did it the other way. We picked a random name here, and then since this one allows us to do anything, we substitute it. Now why is there this restriction that the name must be new? So the existential instantiation, the name must be new. And the reason is that if it weren't, then we could prove some weird things. So let's take one interesting example here. So here's a premise. I'll talk about this in a second. But it says that there exists an X such that fx.ax, fx.ax. Okay. And our second premise is there exists an X such that fx.ox. There exists an X such that fx.ox, and the conclusion is there exists an X such that ax.ox, ax.ox. Okay, so now suppose, this argument's bad by the way, but let's just see what goes on here. Now suppose that we were just work our way through this, and that we wanted to do this, the rule, ignore that rule. So we could write down line 3 here, and we instantiate this. So let's just write fa dot A. And we got that from line 1 by existential instantiation. Okay, so that's okay because we chose something new. But now suppose we wanted to do this. We write down line 4, and we say, oh, we'll use the same thing. No, it doesn't matter. FA dot OA, and we say we got that line from 2 by existential instantiation. Now notice I'm saying right off the bat that this is wrong, but we're pretending. What we're showing what would happen if you were allowed to do this. So now we have AA, we have OA. So we just need to simplify and combine them. So we can write down line 5. We'll flip that around, AA dot FA, and then line 6. Flip that around, OA dot FA. Then we simplify line 7, AA. Line 8, OA, so I'm not writing this down, but you see how I'm getting it. Simplify, simplify. Now we put these together. Line 9, AA dot OA, now exists an X such that AX dot OX. And so notice, this turns out to be valid if we're allowed to use our questionable tactic here. But notice that this argument, if you translated it back into English, it would be a familiar one. And let's suppose that we use F for fruit, A is apple, O is orange. So this says some fruit are apples, some fruit are apples, some fruit are orange, some fruit are oranges. So therefore, some apples are oranges. Some apples are oranges. But now notice that conclusion is false, but these two things are true. It's true that some fruit are apples. It's true that some fruit are oranges. It's false that some apples are oranges. You could do this a million times. Some animals are dogs. Some animals are cats. So some cats are dogs. No. So this is an invalid argument. But notice if we don't restrict the way that we use existential instantiation, then this argument will turn out to be valid. So this is sort of in line with something that you may recall from way back at the beginning of the class. We said, what are we doing when we do logic? And I suggested that we start with something which is more on a firmer footing, namely our reasoning abilities, and then we try to formalize or capture that. And so if we want to preserve the arguments that we think are valid and the ones that we think are invalid, we have to disallow this rule. Pretty straightforward justification. So now we can see that we couldn't do that, as a matter of fact, if we followed the rules properly. So since we used existential instantiation here on our first premise, if we wanted to do the same thing on our second premise, so if we wanted to write down line 4, we would have to pick a new name, we'd have to pick a new name, FB.OB, from line 2 by existential instantiation. And then we could get all kinds of things like FA.OB, and we could eventually, if we wanted to, write down the sentence, maybe something like this, A.O.B. But there's no way to move from that to this. At best, we could say, we could get there exists an X, such that AX.OB, replacing that in that way, and then we might be able to say there exists an X and there exists a Y, such that AX.OY. That would be about the best that we could get here, but that's not this conclusion at all. That's not that conclusion at all. These are very different. And there's no way to guarantee these are the same thing, which is exactly what you want. Now, what's interesting is that the way that we had to show this was invalid, you may have noticed, was by reverting to our old friend, the method of counterexamples. And that's something you may have picked up on by now. But when you're doing proofs and using natural deduction, you're trying to show that an argument is valid. It's very difficult to show that the argument is invalid. And in fact, some of that I've saved for extra credit, but I won't be doing any of that stuff here. But there is a way of using this stuff to try to show that certain arguments are invalid, called the finite universe method, and we're not really going to discuss that, so I leave that to your own advanced study.